In this video, we are going to talk about the idea of absolute and conditionally convergent. So far in these series sections, we have just asked the question, does it converge or does it diverge? Absolute and conditional convergence is asking how well does it converge? So this is something that tells us about the relationship between the convergence and divergence of A sub n series and the series of the absolute value of A sub n. So these are known as absolute and conditional convergence ideas. So what does it mean to be absolutely convergent? A series A sub n is called absolutely convergent if the series of the absolute value of A sub n is convergent. This means that if there's some negatives that are making the series converge, those negatives don't actually matter. If we made the whole series just positive terms, the series still converges. So absolutely convergent if the absolute value series converges. Conditionally convergent is a series is conditionally convergent if the series converges but the absolute value series diverges. We'll see some examples of these two different terminologies. But first, before we do that, what are some steps? Some steps to tell if a series is absolutely convergent, conditionally convergent, or divergent is first, we're going to look at the absolute value. If that series converges, we're done. Then both the absolute value and the regular series converge, and so it's absolutely convergent. If the absolute value series diverges, then we move on to step 2. Then we check, does the series A sub n converge or diverge? Probably with the alternating series test. We're going to get some other tests we could consider. But in general, we're probably going to use the alternating series test here. If that series converges, then the series is known as conditionally convergent. If the regular series diverges, then it's divergent, just as normal. So, taking a look at some examples, we want to determine if these are convergent or divergent. And if they're convergent, if they're absolutely or conditionally. So, to tell absolute or conditional, we first check for absolute. And that is looking at the series n equals 1 to infinity of the absolute value of -1 to the n over n to the 4th. This is the only thing that's negative is this negative 1 to the n. So this is actually a series of 1 over n to the fourth. 1 over n to the fourth series converges by p series with p equal to 4, which is greater than 1. So using this list from above, if the absolute value converges, we're done. It's absolutely convergent. So because the absolute value converged by the p-series test, this is absolutely convergent. And to repeat, what absolutely convergent means is n equals 1 to infinity of negative 1 to the n over n to the fourth. And 1 over n to the fourth. Both converge. So that is what it means to be absolutely convergent. Now, let's look at this next example, the series negative 1 to the n over n. We want to check for absolute. And that is looking at the series of the absolute value of negative 1 to the n over n, which is the series n equals 1 to infinity of 1 over n. This is the harmonic series, which we know diverges by being the harmonic. So, not absolutely convergent. So next we check for conditional. And that is looking at the regular series. Series n equals 1 to infinity of negative 1 to the n over n. We have actually named this off before, and we proved it in a previous video, but this is the alternating harmonic. And we know the alternating harmonic converges. So this means negative 1 to the n over n converges at the series n equals 1 to infinity 1 over n diverges. This is the situation that is quite literally the definition of conditional convergent. So we check for the absolute first, and then we check for conditional if it's not absolute. And if they end up both diverging, then it just diverges. All right, another example. The series n equals 1 to infinity of negative 1 to the n of arctan. First, we check for absolute. And that would be looking at the series of the absolute value of negative 1 to the n of arctan n, which is the series n equals 1 to infinity of arc tan n. We actually know this diverges by the divergence test because the limit as n goes to infinity of arctan equals pi over 2, which is not 0. So the divergence test says if the limit of the sequence is not 0, the series diverges. So we saw this in the integral test and divergence test section. The series of arctan diverges. So it's not absolute. And you may already have the guess of this also can't be conditional for the same reason. So the second one is we would look at n equals 1 to infinity of negative 1 to the n of arctan n. Well, once again, this diverges by the divergence test because the limit as n goes to infinity of negative 1 to the n of arctan n does not exist. Because it's taking the limit of regular arctan and switching that back and forth between positive and negative. So as n is really big, negative 1 to the n arctan n is going negative pi over 2, positive pi over 2, negative pi over 2, positive pi over 2. This limit does not exist, which is not 0. So by the divergence test, arctan n diverges. And so does negative 1 to the n of arctan n series. Since both diverge, this is just completely divergent. Right. And then one more example. We have cosine n of 5 to the n. Now, as we are looking at this one, this kind of looks like the piece that becomes an alternating. However, if we actually look at cosine n and we think through what does cosine have to be, cosine of 1 is going to be some positive number. We don't know what it is. Cosine of 2 is some negative number. Cosine of 3 is also some negative number. And so looking at those, we actually see this isn't alternating. This is not going 1, negative 1, 1, negative 1. This is not alternating, but it's not completely positive either. So not alternating, but not completely positive. Let's make that note. Not alternating. Not positive. So, gotta hope this is either absolute convergent or nothing else. So let's check for absolute. checking for absolute convergence is that we would compare, or we would look at the series n equals 1 to infinity of cosine n over 5 to the n of the absolute value. This 5 to the n is always positive. So in this case, we are looking at the absolute value of cosine n all over 5 to the n. How can we tell if this converges or diverges? Because we've now looked at the absolute value, we've created a positive sequence, meaning we can use the comparison tests. So using the comparison tests, one, as we literally just stated, cosine n over 5 to the n absolute value is always positive. Great. So I can use the comparison test. Now I want to find what I'm comparing to. Well, cosine n over 5 to the n is always less than 1 over 5 to the n, because cosine n, absolute value, is always going to be between 1 and 0. So cosine n is smaller than 1 over 5 to the n, and the series of 1 over 5 to the n equals 1 to infinity, converges by the geometric series test with r, the absolute value of r, equal to 1/5, which is less than 1. So the series we're comparing to converges, and we are directly smaller than the series we're comparing to. So this is the direct comparison test. So the series absolute value of cosine n over 5 to the n converges by the direct comparison test, since the series n equals 1 to infinity of 1/5 to the n converges. So checking for absolute, we actually get absolute convergence because the absolute value series converged. So this is absolutely convergent. So there is another example. It's not an alternating, but we can figure out if it is convergent or divergent by looking at the absolute value. So there is the end of all of our things from the alternating series test. And in the next module, we will get our last two big tests.